Welcome to the video lesson for section 2.7. We're going to look at a couple more aspects or features of rational functions, and then we're going to use everything we've learned from 2.6 and 2.7 to go ahead and attempt to graph by hand some rational functions. To begin with, a gentle review for our x and y-intercepts. To find the x-intercepts, we're going to set just a numerator equal to 0, and then we're going to solve for x, because for every x-intercept, the y value is 0, and y is only going to equal 0 if our numerator is 0. For all of our y-intercepts, we're going to go ahead and plug in 0 for x because, again, for every y-intercept, your x value is 0. And then we're going to simplify that expression, and whatever we get is going to be our intercepts. Let's go ahead and apply that to our first example here. I'm going to go ahead and try and find both the x and y-intercept for my first example. To find that x-intercept, again, what I'm going to do is take just my numerator and set that equal to 0. And this one's going to involve a little bit of factoring. We'll take out an x. If we do, then we get x times x minus 1 is equal to 0. And this should be familiar from Unit 2. We're going to go ahead and set each factor equal to 0. And that will help us solve for our x-intercepts. So I get 2 here. I get x is equal to 0 as one x-intercept, and I get x is equal to 1 as our second x-intercept. For our y-intercept, I'm going to go ahead and plug in 0 in for all of my x values. And if I do, again, we're basically just doing f of 0. We're going to get 0 squared minus 0 over 0 plus 1, which is going to be 0 over 1. And 0 divided by anything is automatically going to be 0. Well, any non-zero number. So we're going to get a y-intercept of 0. And there is actually kind of a coincidence here. We see that we have x equals 0 for an x-intercept, and we see y equals 0 for our y-intercept. And that's actually not a coincidence. That will always happen. So we find our x-intercepts first. And if our x-intercept is 0, our y-intercept will automatically also be 0. They have to be tied together that way. All right, if you look at our next example, we're going to do the same thing. We're going to go ahead and try and find our x-intercept first by taking our numerator and setting it equal to 0. So we have x squared minus x minus 2 is equal to 0. We're going to have to factor this. We get x minus 2 and x plus 1. And then we can set each factor equal to 0. By the way, important to note here, if something is a whole, we want to find our holes first. And we'll talk about this a little bit later, but because a hole cannot be anything else. It can't help us find a vertical asymptote. It can't be an x-intercept because there's a gap in the graph for that value. All right, if we solve these x-intercepts, we're going to get x equal to 2 and x is equal to negative 1. And those are going to be your two x-intercepts. Since you don't have a 0, we have to go ahead and check for our y-intercept. Again, to find that y-intercept, we're going to plug in a 0 into all of our x's. We end up getting negative 2 over negative 1, which is going to be positive 2. So then for my y-intercept, I have my y-intercept of 2. So these points, along with our vertical asymptotes and some other things we're going to do, will help us identify the shape of a rational function and also kind of graph it by hand. We're going to go ahead and attempt to put it all together here. We're going to try and find all of the features for our function here, the holes, the asymptotes, and the intercepts. The first thing we're going to do, as I mentioned earlier, is we're going to go ahead and factor this and try to identify any hole. So if I factor my numerator, we get 5 times x plus 4. And if I factor my denominator, we're going to get x plus 4 and x minus 3. And again, the importance of this is we identify kind of right away that we're going to have a hole. And so what my expression is going to look like now is 5 over x minus 3. And that's the expression we'll use to find all of our features, our asymptotes and our intercepts. I'm going to go ahead and find my hole, though. I know that because x plus 4 is a factor, I'm going to have a hole at negative 4. To find the value of the y value for my hole, again, we're going to go ahead and take that value, and I want to plug it into the simplified expression, which means that we're going to have 5 over negative 4 minus 3, which is going to be 5 over negative 7. So I have a hole at the point negative 4 and negative 5 over 7. All right, we're going to go ahead and try to identify our asymptotes. Again, we're working off of this simplified expression. I notice that I don't have an x in my numerator, but I do have an x in my denominator. So for our horizontal asymptotes, this is going to go ahead and be scenario number 2, where the degree in your denominator is larger, which means by default, I have y is equal to 0. For our vertical asymptote, we're looking at our denominator, this x minus 3. And if I set that equal to 0 and then solve for x, then we're going to go ahead and get x is equal to 3 for our vertical asymptote. For our intercepts, I noticed that I don't have an x in my numerator, so I can't identify any x-intercepts. And that kind of makes sense because of the fact that we have this y is equal to 0 horizontal asymptote. We're not going to cross the x-axis at all. For our y-intercept, though, I can go ahead and plug in a 0 for my x value. And so for our y-intercept, it's going to be 5 over 0 minus 3, which is going to be negative 5 over 3. And what we'd be able to do now is we take these asymptotes, we take our whole, we'd plot them all, and then we'd fill in the gaps by creating a t-table to figure out the behaviors of our function, which we're going to go ahead and do with this next example. Okay, I'll go ahead and let you guys know there are no holes because my numerator and my denominator are not going to have any common factors. So we're going to jump into finding our asymptotes. I'm going to start by finding my vertical asymptote. To do that, we're going to take our denominator and set it equal to 0. And we end up getting x is equal to negative 2 for our vertical asymptote. Oops, and negative 2. For our horizontal asymptote, I'm going to look at my largest terms. All right, we have 2x over 3x. That's going to simplify to be 2 over 3. This is scenario number 1 because the degrees are the same. We need to go ahead and find our x-intercepts as well. So we're going to take our numerator. We set that equal to 0. And if we divide by 2, we get x is equal to 0. And again, that is our x-intercept. Since x equals 0 as our x-intercept, we can say by default that our y-intercept is also going to be 0. Okay, I'm going to go ahead and sketch what we know here. I have x is equal to negative 2 for my vertical asymptotes. I have y is equal to positive 2/3, which is a little difficult to sketch. Could be about here. And then for my point, I know that I have an x-intercept and a y-intercept both at 0. All right, what we need to be able to do now is we need to figure out what our graph is doing on both sides of our vertical asymptote. So I'm just going to put a negative 2 here. And I need to pick some x values, some x values that are bigger than and less than negative 2. So I'm going to go ahead and put in a negative 3 and a negative 1. And we need to identify the corresponding y values for those. So I'm going to find f of negative 3. If I plug in a negative 3, then I'm going to get negative 6 over negative 9 plus 6, which is negative 6 over a negative 3, which simplifies to be a positive 2. So we're going to go ahead and put a 2 there. And if I plug in a negative 1, then I'm going to get a negative 2 over negative 3 plus 6, which is going to be negative 2 over positive 3, which is again just negative 2 over 3. And now I have 2 additional points I can go ahead and sketch. We're going to plot this negative 3, positive 2, and then we have a negative 1 and negative 2/3, which is about right here. And when we sketch our graph, we are going to follow along the asymptotes and just make sure that we curve it to go through our points. The bottom one's a little bit easier to do. We're going to go through our point and our intercept, and again, we're following along our asymptotes. And then for this top quadrant, same thing, follow the asymptotes, go through the point, and we do have to curve this a little bit. And we have then sketched our rational function.
All right, so we're going to go ahead and factor our function here before we try and identify anything to see if you have any holes. I'm going to start by taking out a greatest common factor, take out a 2. And right away I can see that I have different terms in my numerator and my denominator. When I factor them, nothing's going to cancel. So I'm going to go ahead and work on finding my vertical asymptotes. I'm going to take that denominator and set it equal to 0. And then I'm going to go ahead and add 4 to both sides. And then when we take the square root, we get plus or minus 2. So we have 2 vertical asymptotes. I'm also going to go ahead and look for my horizontal asymptote. For that, since nothing canceled, I'm going to go back to my original function here. I have a 2x squared as my biggest term and an x squared as my biggest term for my denominator. So we have 2x squared over x squared, which will simplify to just be 2. And since that's our horizontal asymptote, we have y is equal to 2. I'm going to go ahead and graph my asymptotes now. So we have a -2 and a +2. Then we have a y is equal to 2. And then we're going to find a couple more pieces of information before we start to graph our function. I want to find my x and my y intercepts. So for my y-intercept, again, we know that all of our x values are always going to equal 0. I'm going to go ahead and plug in a 0 for all of my x values. So when I plug in a 0 in my numerator, we're going to get 0 minus 18. When I plug it in for my denominator, we get 0 minus 4. And that's going to end up being a negative 18 over negative 4, which is going to be a positive 4.5. So my y-intercept is 0 and 4.5. For my x-intercept, we're going to go ahead and take our numerator and set it equal to 0. I'm going to add 18 to both sides, divide by 2, and then I'm going to take the square root, and we get two values. We have plus or minus 3. I'm going to go ahead and graph my points here. So we have, again, our positive 3 and our negative 3, and then we have a y-intercept, which is at 4.5. All right, we have enough information on the outside, so we can say that we're going to follow along our asymptotes, go through our intercepts. What we don't have enough information for is the inside portion. So what I'm going to do is set up a t-table, and I need to pick values that are on the inside of my vertical asymptote. So since I have a vertical asymptote at -2, I'm going to pick -1. And since I have another one at +2, we're going to pick a +1. And this will give us a better idea of the shape of the inside. When I take those values and plug them in, again, we're plugging them into the original function over here. We're going to get 2 times -1 squared minus 18 over 1 squared minus 4. That's going to end up being -16 over -3, which is a positive 16 over 3. And then same thing if I plug in a +1, we get the exact same value, which is a positive 16 over 3. And that's going to end up being about 5 1/3, so a little bit bigger than 5. And we can go ahead and kind of sketch our function out. So I know on the inside I have a bit of a parabola here. And then on the outside we're going to follow along our asymptotes, go through our points that we have, which is the intercept. And we don't know the exact shape of our function or how much it curves, but we do know it follows specifically these general patterns. Okay, let's go ahead and look at another example of graphing here. Now for this one, we are going to need to factor it before we can figure out if something cancels. So let's go ahead and work on factoring our numerator and factoring our denominator. So using your favorite factoring technique, whatever that is, for our numerator, what we're going to get is 3x minus 2 times x minus 1, x minus 2. And then for our denominator, we're going to get 2x plus 1, and again, x minus 2. So we see that by factoring this, we do have a common factor in both our numerator and our denominator. That's going to cross cancel. And that tells us that we're going to have a whole specifically when x is equal to 2. To figure out the y value, we're going to plug it in. And again, when we plug it in, we're plugging into whatever is left after we've canceled. And we're also using that expression to identify our asymptotes and any other intercepts. So I'm going to plug a 2 into that expression. And if I do, then we're going to get 6 minus 2 over 4 plus 1, which is going to be 4 over 5, which tells me that I have a whole at 2 and 4/5. All right, for our vertical asymptotes, we're going to look at our denominator. I set 2x plus 1 equal to 0. We're going to solve by subtracting 1 and dividing by 2, and we get x is equal to -1/2 for our vertical asymptote. For our horizontal asymptote, we're going to compare the expressions again from what is remaining. I have my biggest term on my numerator as a 3x, and then for my denominator as a 2x. When I simplify that, we should get y is equal to 3 over 2. All right, I'm going to go ahead and sketch what we have at the moment. So we have a vertical asymptote at -1/2. We're going to do our best to just kind of sketch it in here. And then we have a horizontal asymptote at 3 over 2, or 1.5. Okay, we're going to bring our whole in a little bit later, but for right now what we need to do is find some intercepts. All right, so for our y-intercept, we're going to plug in a 0 for x, and we're going to get 0 minus 2 over 0 plus 1, which is going to end up being -2 over 1. And we have the point 0, comma, -2. And then for our x-intercept, I take my numerator and I set it equal to 0. And we have 3x minus 2 is equal to 0. We're going to add 2 and divide by 3, so we get the point 2/3, 0. All right, we definitely have some points over on the right side. We don't have any points on the left side, so we're going to make our t-table here. And I'm going to plug in some values that are on the left side of our vertical asymptote. I'm going to start by just plugging in a -2. And you can pick whatever values you want, it doesn't exactly matter, but we're going to take that, we're going to plug it into our expression over here, and what we're going to end up getting is a -8 on top, and then a -3 on bottom, which is going to end up being a +8/3. I'm going to go ahead and graph that point. That's going to be a little bit less than 3. And now we have enough information to kind of sketch our graph. Now again, when we're sketching this, we're going to follow through our points and go along our asymptotes. So I'm going to come up, go through my intercepts, and then curve out, and then I'm going to come down, go through the point that we found, and then curve out. And that is our function. All right, now we talked about scenario 3 the other day where we don't have horizontal asymptotes, and what actually happens is we have a slant asymptote. If the degree in your numerator is greater than the degree in your denominator, then f of x does not have a horizontal asymptote, instead it has a slant asymptote. And to find the slant asymptote, what we're going to do is some long division, because when we're done, what we have is our slant asymptote minus the remainder. So to remind you how to do some long division, we're going to set things up here. Your numerator is always going to go on the inside. So we have an x squared minus x. We draw our division bar, and then we have x plus 1 on the outside. Now our goal is to take this x and make it the same as this x squared, and we have to identify what do you multiply x by to make it x squared. In this case, it's going to be an x, so we're going to multiply that x by what we see on the outside, which makes this x squared plus x, and then we subtract. So x squared minus x squared, that's going to be just 0, and then negative x minus an x is going to also be it's going to be negative 2x. Okay, so now I want to take my x and multiply by something to make it a negative 2x. In this case, we're going to multiply by a -2. We're going to go ahead and multiply that number in, and we get a negative 2x minus 2. Again, we are subtracting. Negative 2x minus a negative 2x is going to cancel. That's 0. And then this 0 that we have minus a -2 is going to make this a +2, which is our remainder. Now for your slant asymptote, it is everything minus the remainder, so what we have on top here is going to be the equation of our slant asymptote. All right, we're going to go and set up our next example to try and demonstrate this one more time. All right, so to start this, I'm going to take my denominator because it's kind of long and it goes on the outside. I'm going to write that first. And then we have our numerator. Nope, that's 2. Okay, first step, I want the x squared to be the same as a 2x cubed. To make that happen, we're going to multiply by a 2x. And again, we're going to multiply everything by that 2x, so we now have 2x cubed minus 6x squared plus 6x, and we are going to be subtracting. Negative 2x cubed minus 2x cubed is 0. Negative x squared minus a negative 6x squared is going to be 5x squared. And then negative 8x minus 6x is going to be negative 14x. For our next step, I want this x squared to be the same as a 5x squared. To make that happen, we're going to multiply by a 5. And then again, we're going to multiply that by everything on the outside there. So we have a 5x squared minus a 15x plus 15. And I forgot to bring down my 4. My 4 is going to come straight down here, or my -4. And we are subtracting. Negative 5x minus 5x is 0. Negative 14x minus a negative 15x is going to become just x. And then negative 4 minus 15 is going to be negative 19. When we compare our values now, there's nothing I can multiply x squared by to make it an x. I'd have to divide by something. So that tells me that we are in fact done, and this is going to be my slant asymptote, because everything that's left over is our remainder. So again, the remainder is not included in your slant asymptote. It's just what we had when we were done with with long division. Before we move on, I did forget to do something up above here. I forgot to graph our hole. So what I'm going to do is I'm going to erase this portion over here. I'm going to go ahead and resketch where our intercepts are. And then I'm going to go ahead and put our hole. So our hole was this point 2 and 4 over 5. I'm going to go ahead and put an open circle at 2 and 4 over 5. And then when I go to sketch my graph, I'm going to make sure I go up to that hole, but I actually go through it to demonstrate that we have this kind of gap in the function there. And that's how we'd represent that there's a hole in the function. All right, for this last page, we have some extra examples here. I'm going to go ahead and work them out. You guys are free to try them on your own and then come back and check how you did. So if you want to try them, go ahead and hit pause now and then come back and check and see how you did. But I'm going to go ahead and work them out and just kind of walk through what I did. Okay, so the first thing I did here was identify that we had a hole. I saw that x minus 4 is going to cancel out, so I simplified it to be 2x plus 3 over x plus 1. I found the y value for that hole, and my point for the hole is going to be 4, 11 over 5. I then took my denominator, what was left at x plus 1, I set equal to 0 to identify my vertical asymptote. I took my horizontal asymptote as a ratio of 2x over x, and I got y is equal to 2. And then for my y-intercept, you see I plugged in 0 for x, simplified to be 3, so I got the point 0, 3. And for my x-intercept, I set the numerator equal to x, and I solved and I got negative 3 over 2, so I had the point of negative 3 over 2, comma 0. When I graphed my asymptotes and I graphed my points, I noticed that I had one point that was on the right side, my y-intercept, one point on the left side, which was my x-intercept, and since I had points on either side of the vertical asymptote, I could identify where the sketch was, or where the function exists. And then I put that open circle for our hole to know that the function did not exist at that exact hole. When we look at our second example here, I noticed that since my numerator is not going to factor, there's not going to be a hole, so there's no hole. For my vertical asymptote, we took the denominator and had to factor it, so I got x plus 2 and x minus 1. And when I factored it, I set each factor equal to 0 to get my two vertical asymptotes of x equals negative 2 and x equals 1. For the horizontal asymptote, looking at my original function, I had a 3x over an x squared, and that is by default scenario 2, where your denominator has a bigger degree, so I automatically have y equals 0 for my horizontal asymptote. I went ahead and found my y-intercepts. Because I found my y-intercept to be 0, 0, I know that by default the x-intercept also has to be 0, 0. That pattern exists always. If one is 0, 0, the other one is also 0, 0. So you went ahead and I graphed that intercept, and I noticed that I only had 1 point. So what I needed at this point were a few more points on either side of my vertical asymptotes. So I have a point at negative 3 and negative 1 to get something on the left side and the right side of my vertical asymptote, and then a negative 1/2 and a positive 2 to get something on the left side and the right side of my second vertical asymptote. And what I notice is you can see I have a point here and I have a couple other points. The left side is going to be strictly on this lower quadrant. The right side is going to be strictly on this upper quadrant. And then because my intercepts, my x-intercept and y-intercept were on an asymptote, I see that I have this cubic shape here. And that will generally happen when you have an intercept that is on one of your asymptotes. And then for our last example here, what we notice is that there actually is going to be a slant asymptote. Again, I know there's no hole because I cannot factor my numerator. I find my vertical asymptote to be at x equal to 0. There is no horizontal asymptote because the numerator has that bigger degree, which means I have a slant asymptote. So I went ahead and did my long division. After doing long division, I got that y is equal to 3x. That is everything except that remainder, which became the equation for my slant asymptote. And when we graph that, I just do rise over run. I started at my y-intercept of 0, 0, went up 3 over 1, up 3 over 1, or down 3, left 1, and then down 3 and left 1. I did not have enough points because there were no x-intercepts. I get an imaginary number here, a complex value. And for my y-intercept, I had a 0 over 0. So I had to find points on either side. I found negative 1, negative 4 down here at the bottom, and then positive 1 and positive 4 up here at the top, which showed me where my function exists. Again, we want to go through the points and follow or trace along our asymptotes. So for the top, I went down to my point and then up, and then same thing kind of on the bottom, following my asymptotes and then going down. Okay, that does it for our notes. Go ahead and get started on the homework, and good luck.